This podcast is supported by Siemens, your partner for industrial-grade AI.
So, hello everybody and welcome to a new episode of our Industrial AI podcast. My name is Robert Weber and it's a pleasure to talk to
Peter Sieber. Good morning, good afternoon, Robert, and a nice welcome to our listeners.
Hello, Peter. I'm sitting in the car 20 kilometers from Nuremberg right now because the SPS or PLC trade fair show starts today. So, Peter, if you hear some trucks in the background, please don't let disturb you. But I have already looked in the official magazine of the fair and hardly found any AI or machine learning topic.
Oh, really?
That surprised me a lot.
Well, you will see. I will not be there.
Yeah.
You will be going around. We have been going around. When was the last time we officially did that? That was at Hanover Fair, right? That was 3 years ago, I guess.
Yeah.
It was a big thing, and we still go there. You and I still have, our industrial AI talk. But at that time, as far as I recall, we counted, like 200, and maybe we said, 100 really do something very specific. Now, this can mean two things. If in 3 days from now, at the end of the day, you're going to say, yeah, I didn't see anything. Number one, possible. I don't believe that. And number two, what is possible? Companies are not that explicit about it.
Exactly.
It's probably about the hype curve. So we've moved the top, and we're now going down the slope. And we still not still. I had the same topic yesterday in one of the courses, and one of the attendants was saying all the things that they're doing. So they have come already out of the slope. They're building. And others, maybe it's also the terminology, depending on what you were looking at, right? Artificial intelligence, or were you looking at machine learning, or because that's something still, well, we say industrial AI. Is it maybe machine learning? So maybe the other thing is companies will be showing things, but more like integrated into their solutions, and they offer solutions, and the way they get there, maybe people are less interested in.
Yeah. We will see. I will report in the next podcast about the SPS and the products and the solutions I saw there. So let's start with the news part. Peter, the stage is yours.
Okay, I've got three. First is a team at the European Commission. They have a joint research center. They wrote a glossary of terms on artificial intelligence, a focus on human-centric approach. We're clear, that's what we in Europe are about. For their work, they used existing glossaries from the high-level expert group, from the OECD, from ISO, IEC, Digital Services Act, a couple of other things. They even used, encyclopedias. Specifically, they mentioned Wikipedia. Also specialized websites, blogs. They mentioned Towards Data Science. I read that every now and then. Okay. I didn't see that they looked at our AI pod, the EU website, but who knows? Now, nevertheless, out came 230 terms. 24 of them starting with an A. Yeah, they give an overview alphabetically. Not sure why they do that. None of the terms start with a J, X, Y, or Z. Just for our listeners' information. I'm sure that's very interesting. Now, under A, they share 6 around 100 words long definitions of artificial intelligence. Of course, that's the number one that I was looking at, just for interest. And I would suggest our listeners, if you are not yet sure, also you, Robert, what AI is, go and download the glossary, read all 6, and pick your preferred one.
What is your preferred one?
Oh, well, yeah, I'll tell you. Or as an alternative, I would suggest use my definition, which is only 20 words long. And I'm as modest as to, of course, share that at the moment. So I say AI is when an algorithm in the hands of a human finds patterns in data and makes seemingly intelligent proposals.
Okay.
So that's, as an alternative, number 7 potential definition. But as always, we'll put the link in the podcast notes for you to download the glossary.
Perfect. I have only one use. Yesterday, I was able to have an interesting discussion with two company representatives, and it was about the question of whether data will be accounted in the future. Are they an asset that can be valued, and how do you do
Mhm.
that? And then made a few phone calls and even found someone who could tell us something about
Okay.
it. The date for the recording has not been yet set, but we will report on it because it's very interesting to
Mhm.
account data in your account. That's for companies. I think that's a topic for the maybe
Mhm.
the near future. Yeah.
Um, you've told the story about that somewhere you got a free, so-called free cup of coffee in exchange for your data, right?
Yeah, it was in Switzerland. It's a restaurant where you
Mhm.
can exchange data for coffee. But I think when you have merger and acquisitions, the topic
Mhm. Right.
data is a very important topic. I think when Microsoft bought LinkedIn, it's all about data. It's not about the technology of the
Mhm.
social network. It's
Mhm.
all
I
about
guess.
the
Okay.
data of the people who join or who use LinkedIn. So data is an important
Mhm.
asset, and maybe for industrial company, it will be accountable in the future. Yeah.
I heard the same story said about I don't like using the name of the person, but the one that bought Twitter, that was for the same reason, for for not for
Yeah.
whatever reason. There may be hundreds of reasons, positive, not so positive, but one may have been for the data, the data that people generate through using Twitter.
Yeah. So I will do the recording. Maybe I will also contact some banks or some accounting companies. We have a lot of accounting companies in the world. Maybe it's an interesting topic also for industrial companies.
Yeah, looking forward to.
Yeah. Peter, go on.
Second one is about autonomous driving. The
Mhm.
Ford car company, they announced that they will wind down Argo AI,
Yeah.
which they had together with Volkswagen set up for developing level 4 autonomous driving technologies. Now, this decision has a number of analysts call out that self-driving cars uh, are not going to happen, at least not truly autonomous
Mhm.
vehicles in our
Mhm.
lifetimes,
Mhm.
whatever age of those analysts were. If they're the same age as I, that's, it's a different meaning from, a 20-year-old person, and not at any kind of scale. So the only brands that also I know of still operating driverless. At the same time, I did see, it was on LinkedIn, maybe you've seen, one of the people that we follow, driverless vehicles on public roads, but of course strongly limited by
Mhm.
area, also by
Mhm.
time.
Mhm.
Waymo and Cruise, without just now going into the details, and Uber and Tesla, they have had their share of driverless and co-driver casualties, and of course they're under scrutiny of the U.S. government. And then the only brand that I know of, having a level 3 product is our, good old Mercedes
Mercedes. Yeah.
level 3. I think it's called the EQC. So in the end, maybe as I stated in my booklet, how AI is changing our lives, 100 questions and answers, we say, maybe we're sooner going to see autonomous flying cabs.
Yes. Yeah. Sure. But I think it was not the EQC. It was the EQS. But I'm not sure.
Oh, really? Okay.
Yeah.
Okay. Yeah. I'm not that strongly aware of cars.
You're more in camping. Yeah.
Exactly,
Ex-
exactly. I still drive when every now and then. Well, but normally I do use public transport.
Yeah.
The German ICE fast train with including internet connection and capabilities for working and relaxing.
Sometimes. If sometimes if it is
Working
on
and
time
relaxing. Yeah.
and if it is working.
I've got a final one. Final one. I started reading a book called Game Changer. One or the other listener may have done the same already. Not sure how old it is. I think the work started 4 years ago, actually. It's about AlphaZero's groundbreaking chess strategies and the promise of AI by Matthew Sadler and Natasha Regan.
Mhm.
I would like to share some quotes out of it first, and they're from 2018, as I say. So the first is Gary Kasparov. He gives the introduction. He says, I always say I was the first knowledge worker whose job was threatened by a machine,
Mhm.
referring to his loss to IBM
Yeah.
Deep Blue in 1997. And then he says, instead of using machines as tools, machines become the experts and humans will oversee them. Oh,
Mhm.
that's his thought. And then I got a couple of quotes from Demis Hassabis. He's the DeepMind CEO, right? Very, very interesting character. Whatever you can get on YouTube, anywhere else, I can strongly suggest any listener to take in what he has to share with us. He is, for me, at the same level as Andrew Wing. Those are the number one and two in my mind people that show us the world where AI is leading us. So he's the DeepMind CEO. Alpha, he is the brain, behind, together with two, three other guys, AlphaGo, AlphaZero. And he says, number one, we want to solve intelligence and then use it to solve everything else. And on the path towards that ultimate goal, we perhaps surprisingly use games. Now,
Mhm.
that's what I want to comment on. And then I finish with two, three more quotes from him. Why do I want to comment on it? Because as you know, I'm on a kind of a AI chess or chess
Yes.
AI, right? I restarted playing chess like a year ago. You said you've been playing chess in the past as well. So I do. I train a bit. I play on liches, and I combine this, renewed or additional chess knowledge with my basic knowledge on AI.
Mhm.
Seeing other chess students and professionals, kind of forced to learn by heart thousands of openings. I think most of our listeners at least have heard about, something called out like, the Italian opening, the
Yes.
Spanish or the Berlin or the Queen's Gambit,
Yep.
after which the movie in 2-3 years was called. Now, that thought is not very, what should I say, not very interesting to me. I like very much what I'm doing, but this idea of then, almost kind of needing to go back to school and learn by heart, that's not interesting for me at all. So, and then I start comparing this approach with AI, right? So, and I would say it sounds very much like the original 1960s, 70s symbolic AI approach. You
Yes.
recall, and that then ended up in the AI winter, right? Because it was all about describing, rules based symbolic.
Yep.
Then after the AI winter came machine learning, unsupervised deep reinforcement learning. That's what Demis and DeepMind are using, and these algorithms they look at millions. Now, for us humans, who knows? Maybe we can look at tens or hundreds of thousands of games
Mhm.
and learn, but in a completely different way. That's my hypothesis. That's my hypothesis that there's going to be a new way of moving forward in chess for me and others. And I'm very encouraged by the fact that reading in the book, I didn't know that. I've seen that, chess world champion Magnus Carlsen. He has started looking at those games and he has started using some of the specific approaches, moves
Mhm.
from his games. And now Magnus is already the world champion. I'd still need to get there. But my feeling is that we will see a new way for humans to learning from AI.
Do you record a chess podcast too, Peter?
No, I was going to write a booklet.
Okay.
But not on the combination. I still may do that as well at some point in time. Well, as you and I know, we know how much time goes into writing a booklet. Now, I
Absolutely.
was I was going to write a booklet on verbs. There was a
Okay.
one on German chess verbs, but then I saw that already exists. So no, I'm not going to do that.
So you need to do a podcast, I think. Yeah.
Yeah, who knows? Who
Yeah.
knows? But again, the reason for me this sharing here, and of course we do share in our a news update, things that are very specific to industrial AI, but we do, as we did today, and we do other times, share also thoughts that are, completely far away, likely, as Demi says at the beginning,
Yep.
games. What about that? What can we learn from games? Well, I believe that we and all of our listeners listening to our industrial AI podcast can learn a lot, can learn
From games.
very many things. In this case, well, in this specific case, from games. Yeah, right. I think really the way that it happened, with Kasparov, that's 1997, that's 25 years ago. And chess was the first kind of, let's say, let's not call it a market activity, games that was completely changed. And I think by looking at what is happening there, and the good thing is that there was an initial thought that, nobody was going to be playing chess or Go anymore. That's
Yep.
completely not the case. There's now in chess, there's like 4 or 5 times as many people playing chess, and AI has completely reinvented kind of and gave a new push to the game.
So now let's switch to the main part, Peter. You spoke with Michael Haft from Explain Data.
Right.
What was it about?
Oh, it's about the difference between correlation and causation. And somewhere in the interview, I recall that, as I was, working here within our industrial data intelligence team, that we had my colleague, Dr. Albert Krohn, Albert, if you're listening, and he would say us every now and then, now all together, correlation is not the same as causation. And that's some kind of quote that many listeners will have heard somewhere. I still don't know where it originates from, but people who kind of study statistics or are somehow related to correlation. And Michael, he has a specific approach, and he says, the very fact that we're not looking at causality within artificial intelligence. So he says specifically what we have been doing many, many times here in our podcast. We look at predictive maintenance analytics, and we find out, oh, there is a problem, and the algorithm is predicting that, 10 minutes from now, 1 hour from now, something is going to go wrong. But we need to go the next step and find out. We need to find the causation for it. And he is suggesting that that is not taking place or not taking place enough. And so he is explaining us the difference between correlation, causation, and he's showing a path forward for more strongly including causation into artificial intelligence.
I'm really looking forward to hear that this interview. Thank you, Peter. It was a pleasure. I will now join the SBS, and maybe I put my headphones on and will hear the main part. To our listeners, enjoy the main part, and thanks for listening. And thanks, Peter. Greetings to Munich.
Have a good time at the SBS. Say hello to our friends and
Yes.
hello to our listeners that you may run into.
Sure. Bye-bye.
Bye-bye. My guest today is Michael Haft. He is the founder and CEO of Explain Data. Hello, Michael.
Hello, Peter.
Michael, please tell our listeners, who are you, where are you from, and what do you do at Explain Data?
So basically, Explain Data is a startup company here in Germany, close to Munich. And our topic is understanding cause and effect relationship based on observational data. And I'm certainly going to explain along this podcast what that means.
Okay, sounds good. Yeah, maybe as a quick introduction, what are the kind of things that maybe I think the name is kind of in the game of Explain Data, but maybe you still want to explain the next level in your words. What it is exactly that you're doing. Maybe for that reason, the kind of customers that you have or that you are looking for, the kind of applications and use cases.
Yeah, maybe let me start this way. I want to argue, why is causality important? And I think it's evidently important, but it's not that much prevalent in the domain of artificial intelligence, and we're going to change that. So let me start in explaining why causality is important. Let me explain it by means of starting with predictive modeling. So everyone is talking about predictive modeling at the moment, and predictive maintenance in the case of Industry of Things, which basically means predicting the probability for a machine to fail. But the next important question might be, once I know that there is a machine which is likely to fail, what can I do about it? And that's where basically predictive modeling ends and causal discovery starts. Because your goal then is to intervene into a system, to set some actions which avoid failures. And the interventions which you do, they should better be in a cause and effect relationship to the target, to the failure variable. So that means, and predictive modeling doesn't tell you anything about a cause and effect. And causal discovery is kind of the next step. It's not predicting the probability to fail. It's going to tell you, what do I need to do to change the failure probability? And I would argue that is evidently important. Maybe it's an even more important question, not knowing the probability to fail, than what can I do about it? And that's an element which I believe is still missing in artificial intelligence. So causality needs to become a very important element of artificial intelligence. That's our opinion, and that's our mission to change this.
Very good. I'm completely with you. I've been dealing with predictive for many, many years. And I guess in the end, when algorithms were showing certain, I will use the word for the moment, certain correlations, you will talk about that topic. It was always the domain expert who was then giving, and again, I say this very carefully, causal relationship to the combination of certain variables. But you're going to explain if that was correct or not. Let's just really start there. Let's stay with the cause and effect key to artificial intelligence, as you said. And what I was reading also on your website, uncover cause and effect relationships in your real world data. Now, this sounds like, and in my case, it was, 4 or 5 years ago, not too far away from where you are based. We were in a startup, industrial data intelligence. And my colleague, Albert Krohn is his name, and he would at regular intervals tell us, and now all together, correlation is not causation. And you know exactly that. I don't know where it's from. Maybe you want to tell us. So what I would like to do is that you take our listeners with you, and that you start explaining us what is exactly, and it's now a play on words, the relationship between, cause and effect. In other words, what is the difference then between correlation and causation? And on your website, you're using this perfect example of the gray hair, the glasses, and age. And maybe you want to explain our listeners along those lines.
Right. So indeed, this word correlation doesn't equal causation. It's used very, very often, but simultaneously, it seems to be one of the most frequently ignored truths also. People are very often drawing a conclusion based on correlation, and what they indeed want to know is a cause and effect relationship. And example on our website with gray hair and glasses, maybe I walk you through that just as an illustration. So I don't know, you might have gray hair, Peter.
And you have actually.
so do I. And I need glasses for reading. I don't know whether you need glasses for reading.
I do as well. For reading.
You do as well. You see, so obviously, gray hair and glasses, those two variables are kind of correlated. But they are not in a cause and effect relationship. You might try to put your glasses aside to avoid your hair becoming even more gray, but that probably wouldn't have any effect.
Exactly.
And you know why? But because there is a so-called common cause for both. So it's age. The older you get, the more likely you have gray hair, and the more likely you need glasses. So that's a common cause for both, with causing both gray hair and glasses, and that results in a correlation between gray hair and glasses. But there isn't a cause and effect relationship between the two. So that illustrates the difference between correlation and causation. And for building a predictive model, you can build a predictive model perfectly well based on correlations. So, for example, you might be running a shop on Amazon and you don't know the age of your customers, but you know some of the customers have bought glasses and you want to sell them a product for coloring the hair. And you can build a predictive model who is likely in need of a product for coloring your hair. So you can use the information about glasses to estimate a probability who might want to have a product for coloring your hair. So a predictive model can be built perfectly well based on correlated information, but it doesn't tell you anything about cause and effect. And so about understanding cause and effect largely means understanding potential confounders. That's the technical term for age is a confounder, cause is both. And there might be many of those confounders. Age is just the most evident variable. There might be many others as well. So stress in your job might cause your hair to become gray. And because you have so much stress in your job, you're sitting in front of your computer all night long, and which causes you to finally need glasses. So there might be many of them, and you need to know all of them to get an idea about potential cause and effect relationships.
Can you give us maybe an example or two just out of our real life where all of us, where listeners, maybe until you started studying the topic yourself, made kind of, you drew false conclusions, that correlations were actually causations?
Yeah, there are many funny kind of examples.
Oh,
You
please
wake up
share them.
you wake up in the morning and you have your shoes still on, and you have a headache, and you might conclude, oh, sleeping with shoes causes headaches. But the real confounder is that you have been drinking in
All right.
the evening before, and it causes you to fall into your bed with your shoes on, and the next day you have a headache. So
Oh, that never happened to me. I'm not sure what you're talking
it's also not to me, but that's kind of
Okay.
there are many of those amusing examples, but there are many others certainly as well where people draw false conclusions based on correlations. And basically, the world is full of correlation. Let me jump to the healthcare domain, for example. So in healthcare, we have around about a couple of thousand, up to 10,000 different drugs which your doctor can prescribe to you. There are about a couple of thousand, maybe 10,000 different diseases, so-called ICD codes, which a doctor can assign to you. And so it's 10,000 times 10,000, it's 100 million pairs of variables. And whatever pair you pick, you will likely see a correlation between the two of them. And simply because for most of the drugs and for most of the diseases, it holds that the older you get, the more likely you need some of those drugs and the more likely you have some of those diseases, which again results in a correlation, as in our gray hair and glasses example, which means there are hundreds of millions of correlations in those data, and nearly all of them are more or less meaningless, and are not telling you anything about cause and effect. And certainly people very often draw false conclusions on cause and effects if they observe a correlation. Also in healthcare, but not that much in healthcare, because in healthcare it's indeed very well known in between, or people are very aware of the fact that correlation doesn't equal causation. But that's different in other industry, and it's also the case in Internet of Things or in manufacturing. So the engineer is very much inclined, if he sees a correlation, he concludes on a cause and effect relationship because he typically does experiments. In an experiment, it's still true. If you do an experiment in a controlled environment, you may conclude, if you observe a correlation there, you may conclude on a cause and effect relationship. That's also what the healthcare industry does. They are doing a randomized controlled trial, for example, an experiment, and under such experimental conditions, you may, from a correlation, conclude on a cause and effect relationship. But that's exactly different in case of so-called observational data. If you're just observing a system and you're not doing experiments, in that case, it's different. If you just observe many people, and whether they have gray hair and glasses, from those observational data, you may not conclude on a cause and effect relationship.
Let's stay with that for a moment, because the more general question, can we measure causation, or, staying with then the observational data, can we, out of the observational data, detract the cause and effect relationship, or what does that then mean for the way that we collect data? And maybe, it's okay for the beginning to stay in healthcare. I think all of us can follow, and then later on we can kind of slowly move into industrial environments and specifically refer back to, again, my personal experience. And we've been using it a long, long time. Always like algorithms look into data from the last, couple of weeks, months, maybe even a year, find certain relationships, and most of them the domain expert can recognize. And then there is something there that the engineers, let's say in this case, the engineer as the domain expert, needs to look into. So maybe you can comment on that.
Right. So everyone knows that definition of correlation. So if you have a data set, a table with 100 columns and a couple of thousand lines, every student knows how to compute the correlation coefficient. Anything he needs is just those 2 columns to compute the correlation coefficient. And the question is there a similar precise definition for causation? And unfortunately, there isn't. So basically, correlation has a precise definition, causation, unfortunately not. And indeed, causation cannot be proven based on observational data, at least not in any real-world setting. In a theoretical setting, maybe, but in a real-world setting, usually not. And the reason is what you need to understand potential cause and effect relationship, you need indeed very, very comprehensive data. So as explained in our gray hairs and glasses example, if you don't know the age of our visitors, we might falsely conclude on a cause and effect relationship between gray hair and glasses. But as said, it might not just be age, it might be stress in your job, nutrition environments, on whatever. And at the end, you need to know kind of everything to rule out any potential confounders. And if I just can't explain an observed correlation by means of some confounding information, so however big data I have and however hard I search, I just can't explain a correlation, then it's still not a proof for a cause and effect relationship, but it's a very likely candidate. So that shows you that there's no precise mathematical definition, but a kind of correlation is the opposite to causation. For correlation, you need just 2 columns in the table. For causation, you need to know just everything else, because if in all the information which we have, you can't find a confounder which explains an observed correlation, then it's a likely cause and effect relationship.
I believe that we may not want to go there, that there's even like a more philosophical school of thinking that causation does not exist or whatever, but you may want to comment on that just in a moment. What I'm going to do in the future, I do trainings, I do introductions to artificial intelligence. So the first question always is, what is artificial intelligence? And then I go through a couple of ideas and thoughts from the past, and then I conclude. And the next question is, what is intelligence? And I say, well, I'm not an expert, but we do not have one single definition of intelligence. Number 2, we do not have one single definition of artificial intelligence. For that reason, the European Union at the moment has, 1-page description of what AI is. And in the future, that's my point, I'm going to add, if I'm then going to talk about correlation and causation, I'm going to add to say, and we do not have one precise definition of causation. This thing that I just mentioned, and I never really understood that. We may not want to go there too deeply, but there is a school of thought that says, causation can never be. Do you understand what I'm talking about? What does it refer to, like philosophically?
Yes, definitely. Trying to define the term causation is indeed very difficult, and at the end, you might be able to define it on a very physical level. So I've been studying physics, and certainly the concept of cause and effect is a very important one. And if you go down to a physical level, there are certainly cause and effect relationships. But we are talking about observational data on a very, very different level, and defining the term causation based on observational data, it's basically not possible. And that doesn't mean that it's not important for artificial intelligence. And there are a couple of different kind of semi-mathematical definitions. And okay, it's not possible to define it in a rigorous mathematical way. Nevertheless, the concept is important and needs to be an element of artificial intelligence.
So let's see how we get at least in the direction of it, or close or completely. I mean, you have introduced, I understand, the theme of object analytics. What does it stand for then?
So as explained, for understanding potential cause and effect relationship requires very comprehensive information, because otherwise we are at the risk of missing some important confounders. So in terms of the 3 V's of big data, it's the third V. It's big data, sometimes defined as volume, velocity, and variety. And we need a big variety of information about the object in focus of analytics. And that's, as I said, causation is kind of the opposite to correlation. For correlation, I need just 2 columns. For causation, I need everything else. And everything else necessarily means it's not a flat table. Because imagine, for example, the object in focus of analysis is the patient. And you have electronic health record, for example, with prescription, diagnosis, procedures, operations, lab values, genetic data, whatever. That would never fit into a flat table. Necessarily, it's a complex data schema, or in other words, it's a complex object which you need to analyze. And that's what we indeed do. So basically, for implementing our causal discovery algorithms, we have also implemented our own kind of database, which we call an object analytics database, where all the important information for a customer, for example, is attached to the object in focus of analysis. In healthcare, it's the patient. In industry, it's the part which is manufactured in a manufacturing line, or the machine. And whatever the root object is, you can attach a number of different data streams to this root object, and having all information in one place together, stored in a kind of object, you can analyze this object holistically, which definitely is a basis, as explained. It definitely is important for causal discovery, so not to miss important confound.
Now, does this concept of the need for holistic data hold true for the example of healthcare you mentioned? Let us move into and compare with, and also already split in manufacturing between discrete manufacturing and process manufacturing. So the point is, again, just built on my personal experience, and having had many interviews on the topic. So if in discrete manufacturing, I have a number of variables, if there are 10 or 100 or 150, and from my experience, they would be brought down even to the most relevant ones. So we can talk about that. And then we would arrive to a point where, algorithms would find certain, let's say, to relations. And for me, then always the domain expert was, and probably still is, the person to then say, oh, I don't know what that is. Maybe, a sensor was dirty or something, or would then say, oh, that's amazing. We've looked at this for a year or two with a complete team who had no idea. And now we see the relation of A, B, X, and Z. And now we understand what's happening. So from my understanding, you should please comment, is that they are finding this relationship between, the correlation and causation. And then the third category for us in this podcast, it's 2 categories. It's discrete manufacturing, I just discussed. And the other one is process industry, where, again, from my personal experience, we did come typically a lot more complex, even if the algorithm would find certain correlations, it would be so complex that we would need to do, my colleagues, not me, my colleagues would need to do root cause analysis. So I'm asking you for this need for holistic data. Is that always the same, or does it really depend on the environment, healthcare, discrete, or process manufacturing?
Yeah, I definitely believe that it's always the same. So if you don't have holistic information, you're certainly going to miss important confounders, because you just never know where those confounders might come from, and the need of very holistic information. So I'll give another example. Maybe we have recently been trying to understand who is likely to be infected with COVID based on the data of a public sickness fund. And so at a very naive first look, it seemed that women are more likely to be infected than men. But only as soon as we attached information about the employment situation, it turned out that it's the employer, or if someone is working in a kindergarten or as a teacher, he's more likely to be infected, and typically those are more the women than men. So you see, quickly drawing very wrong conclusions on cause and effect. Women might be more likely to be infected simply in case of if you have missing information. And so it again shows that you really better need to attach just everything you know about your object and focus of analysis and let the machine search of all this information to come up with meaningful cause and effect relationships. And even then, it's typically you never have complete information. If you have just complete information, then you might indeed be able to prove a cause and effect relationship, but that's not true in real world data typically. And that's where the expert comes in. So I want to avoid the perception that causal discovery is just an algorithm where you hit a button and you start the algorithm, you get the results. Definitely understanding cause and effect relationships requires the involvement of the expert. The expert needs to be able to make interpretations of the results. He needs to be able to, for example, say, okay, I just can understand this factor. Show me the next best alternative to that. Or he might needs to be able to do things like formulate his assumption on, I would have expected that this and this factor is causing COVID-19 or whatever. And the machine is going to explain why it doesn't, because it's correlated to others, and the other factors are the direct cause and effect relationship. So definitely causal discovery is not just an intelligent algorithm. It needs to be more than that. It needs to be a concept. And in that sense, it falls into the domain of explanatory AI, explaining these factors to an expert, giving the expert the opportunity to give feedback, and in this interaction with the expert, finally arrive at meaningful results.
Okay, I'm very happy to hear that, because I've been kind of almost like teaching, praying to the crowd for many years, that I've been saying, with the changes we're in the middle of, Industrial 4.0, artificial intelligence, data science, machine learning, the role of what I call the domain expert and it doesn't matter. I have been saying in what market, if it's in a healthcare, a house doctor, as we call it, it's called a PG, I believe, in international terms, or in industry, the person in charge of the production line. Because I've sometimes become more philosophical to say, if we would leave, if that would be possible at all, to the decision if a correlation is a causation to an algorithm, then it's kind of that we humans take a step back and leave the complete world to algorithms, which is, I believe, we should not be doing that. Now, tell us how we can use your approach in maybe medical, but if possible, moving to an industrial environment. Does it mean that we need different data from what we have today, other data? So today, typically we have, PLC, we have sensor data, we have temperature, we have pressure, all those kind of things. Do we need a different approach? And is that depend on discrete manufacturing or process manufacturing?
Yeah, maybe let me start quickly with the medical case, and we then jump to the industry case. So the real world data are piling up more and more. So in public sickness funds, for example, are collecting lots of data about their patients, millions of patients with all the diagnoses and prescriptions. But also electronic health records are becoming more and more used, and there are lots of so-called observational data or real world data piling up. And there is definitely a big opportunity in those data, because so the pharmaceutical industry needs to spend huge amounts of money on clinical trials to prove a cause and effect relationship, to prove the drug is causing to your disease to become better and not to have some side effects. But that's very, very expensive. And on the other hand, those real world data are piling up and are largely unused for better understanding the effect of drugs and treatments under real world conditions and potential side effects. And also certainly to save money, and so not to be able to understand cause and effect relationships, not just in terms of randomized controlled trials, but in terms of real world data. And there are a couple of examples already. So we have a couple of nice success stories there on side effects of fluoroquinolones, for example. Soon are coming more. But let me switch to the industry domain. So basically, in industry, from my point of view, data are still underutilized. There are lots of data are collected in a SCADA system, and definitely those data are complex structured. It's not a flat table. Any kind of real-world data, electronic medical record, as I said, it needs to be a complex data schema, and it's not a flat table. And that's also holds true for data from production line, from the SCADA data of a production line, for example. And those, on the one hand, I believe still even more messy than the data in healthcare, and if a cause and effect point of view, still underutilized. And I hope that is going to change soon, as there are numerous opportunities in that context.
So one way, as at least what I understand, moving towards holistic data, maybe we have the data, as you say, we're not using it. Another piece of experience is that where I have been personally involved, and some listeners will have heard that before, that my colleagues, the data scientists, would typically look at reducing the data through statistical means. The easy way of saying, if I have the temperature in Celsius and in Fahrenheit, I probably only need one of those variables. I can throw one away. So reduce, from 150 variables maybe to 5 or 10, which were, the representative, the top features, and then reduce from, terabytes to, whatever, gigabytes, for example. And that was only to be at that time, running models on a notebook rather than in the cloud. Now, combining that with the need for doing something good for our climate, which is happening, and we see it all around us, where people are saying, AutoML, oh yeah, wonderful, you can run 1,000 or 10,000 different models, but if you only need to run it once, which is certain USP of companies providing certain approaches, then they say, okay, instead of 10,000 times energy consumption X, I only have it one time. So where is the truth, so to say? Should we be looking at both, taking the best of both worlds? Or?
For one specific task, predicting a specific kind of a failure of a machine, maybe 10 variables are sufficient. For predicting another kind of a failure, it's probably 10 others. And so I think it holds true in case of a very specific target which you want to predict, but across all different targets, I would say no. And the other thing is, typically upfront, you don't know which of the 10 are important, and that's kind of what causal discovery does. So causal discovery, as explained in healthcare, we have 100 million correlations to. You might imagine a flat table with something like 1 million columns, one column for each product, which is prescribed in Germany, and you have 10,000 different products and 10,000 different diagnoses. And so turning this into a flat table would be a useless endeavor. But what causal discovery basically does, it's kind of doing a deep search of a complex data model, and it's telling you how to boil down this complex data model to 10, 20, 30 relevant variables, which you could imagine as the columns of a table. It's never done physically. It's just done virtual, in a virtual sense. And it's going to give you those 10 columns or those 30 columns, which are important to predict a specific target and which are potentially cause and effect related to the target.
What does that mean then? So what is it then that you offer potential or your customers? Do you go to them? Do you support them on site? Is there an off-the-shelf solution? What are your tools, a specific platform that you use? Or
we are offering two assets: the causal discovery algorithms, which are built upon our object analytics database. So you need to install our object analytics database. You can install it locally on your notebook computer. It's a technology which runs on a small device as well as on a large devices. You can install it as well on a big server with 128 cores. That's, for example, the case in healthcare. We have one partner which is marketing the data which he collects from pharmacies, basically all the anonymized data of 60 million patients with an order of magnitude 3 billion prescribed drugs. And those are sitting on an object analytics database on a server with 128 machines, cores. And so this object analytics database in itself is already an asset. It allows you to explore a complex object in a descriptive way very effectively across different data streams, across diagnosis and prescriptions. And in particular, it allows to run the causal discovery algorithms. And those are the two assets which we bring to the table. The one is our object analytics database, an asset on its own, indeed, and our causal discovery algorithms built on top of it.
Right. So maybe you can kind of walk us through it. I think you have an example of a cylinder head production. You're looking for root cause analysis, how that would work. Where are you involved? I mean, were you involved in, providing your thoughts and ideas to this potential customer, and at some point in time they can take over themselves? Who is that then? Is that then a typical domain expert? Is it a person that needs some certain data science knowledge or introduction by yourself? And what are the different steps that this person will take?
There are a couple of examples, success stories from the healthcare domain, and in between also in the industry domain. So basically, we have started in healthcare because most of the algorithms, are standard algorithms as propensity scores and so on, has been developed in healthcare, and that's also where we started. But we increasingly like the industry domain because where we had a number of very interesting success stories. One of them, for example, together with SW, Schwäbische Werkzeugmaschinen, which are equipping production lines with their machines. And one of those production lines is at Scharpmüller, and they are producing cylinder heads, for example, for Daimler. And those are manufactured in a number of different steps, something like 20 different steps, where each of those steps has certainly a number of process parameters. So you see, you quickly getting into a large number of data along a whole production line. And at the end of that production line, there is the leakage test. You need to test whether the cylinder head is leaky or not. And certainly, when we started, it was up to 10% of the parts which have been produced failed in the leakage test. And then the question is why? What are potential causes which cause this failures? And they didn't have a good transparency into the data, not even from a descriptive point of view, and definitely not from a causal discovery point of view. And there we have a number of very interesting success stories. For example, it turned out that the part temperature is not just correlated to later failures in leakage tests. It's likely indeed be in a cause and effect relationship because we couldn't find any confounders. So we needed to conclude that this part temperature indeed causally affect the result of the leakage test. And that was indeed finally confirmed. Basically, it turned out that the leakage test didn't work properly at low temperatures. If the part temperature was too low, it's not that the part was leaky, but simply the leakage test didn't work properly. They didn't know that. And a couple of other factors which we could pretty quickly dig out of those complex data. And so it's now going to this next step where those algorithms are constantly monitoring this production line. So they are running in the background whenever new data are loaded. The causal discovery algorithms are scanning the data. They are comparing the causal results of previous runs to the most recent run, so to report potentially new upcoming causes for production failures. And certainly, if a new cause is coming up, an alert, an email is sent to the engineer. Because again, he needs to make the interpretation. It might, for a number of reasons, it might be wrong. He might want to reject it. But we can kind of search the needle in the haystack from the millions of correlations, just report the few potential important causal relationships in kind of an early warning or an early notice to the engineer. And the engineer himself, he doesn't need to be a data science expert. The people at Schwäbische Werkzeugmaschinen who install our technology at the customer side, they certainly have to have some data science skills.
Very interesting to hear. And when you talked about the 20 steps that they have, I can, again, from experience, relate to your proposal for, the holistic data that we have been doing a kind of a root cause analysis in a surface mount technology SMT production line. They're not 20, maybe they're more typical, like 10 steps, I believe. We would have only general data, the metadata from the PLC and from the complete production line. And already at the beginning, my colleagues, they were suggesting that that data may not be sufficient. And it turned out to be there were some very interesting statistical pieces of knowledge that we could share, but we needed more. It goes this direction, I believe, of what you're saying. So we were asking for the machine data, so of these, 10, 15 different machines. We didn't get them in the end, so we could not actually finish the root cause analysis. But it sounds very similar to what it seems your approach that you're taking there. Normally, at this point, we're getting to a close. I would be asking for the machine learning environment, but I feel that's different for you. I still ask, what is the development environment maybe that you're working in the end, resulting in your assets for causal discovery?
Guess you're asking about the technical setup of the system.
Yeah, normally I would want to know, are you working in the cloud, on Azure or Google or AWS? Okay. Are you working with, certain frame structures, Python or whatever? But it feels that you're, that's my hypothesis assumption, that you're maybe working in a little bit of a different setup there.
I don't think that our setup is very unusual. So it's basically a very standard setup. So as I said, you can run our technology in a client server setting where the object analytics database sits on a huge machine, and there are certainly interfaces to it. So there are a number of different interfaces. There's a web-based interface or simply a JavaScript interface where you can build your own applications against that object analytics database. So it helps you to just quickly develop custom applications, leveraging the strengths of an object analytics database. There is also a Python interface. So from your local Python environment, you can issue queries against the object analytics database, get the results back into a pandas data frame, run the causal discovery algorithm from within your Python environment. That certainly addresses the data scientist. We definitely want to be open to the data scientist. So the data scientist can install our technology completely locally on his computer or on a huge machine in a client server setting, than treating the real big problems of the world. And it's a pretty standard technology. So it's basically containerized, which means that it's wrapped, for example, into a Docker container, and that Docker container can be installed quickly, more or less anywhere. In particular, it can be installed on a cloud-based service. So this project on the cylinder head manufacturing, it basically runs on Amazon Web Services at the end. So you see, that is kind of standard technology, which you can very quickly deploy in different environments.
Sounds great. So coming to a close, I was going to ask you, where do you see causal discovery? But I think you've told us we're at the very beginning and you want to change it. So let's change the question towards how then, what is your approach to say that, and are there any difference, by the way, in where we look today on causal discovery in, let's say, Germany, Europe, in relation to US, China, the world? That's one thing. Where are we today? How are you going to be looking at changing it? And, feel free to add any, details that you may want to regarding your company, your team, where you're based, if you're looking for colleagues, whatever.
Basically, I think causal discovery is just at the very beginning. And that opinion is confirmed by a recent hype cycle, a Gartner hype cycle, which has been published only a couple of weeks ago, where the term causality first time appeared on the Gartner hype cycle on artificial intelligence at the very...
On the left bottom there, right?
On the left bottom, exactly.
Yeah. So, for those people knowing the hype curve, we've talked about before.
Yeah, and then those people who know what the hype curve is, they know what it means. It's a very new topic, which, however, is likely to be very, very important and will get some visibility soon. And there might be, I can very much imagine that there is soon the typical hype in causal discovery might climb up the hype cycle very quickly in the next month and years, because I think it's more than justified, because I indeed believe that the topic causality needs to be an important element of artificial intelligence. So if not that, what else? If something, you perceive something as intelligent if it helps you to achieve your business goals, but to achieve a business goal and to set the correct interventions to achieve it, you need to know something about cause and effect, because otherwise you wouldn't be able to intervene into a system in an intelligent way. So it's more than justified that causality is at the start of the Gartner hype cycle. So I expect that it's going to go up there, and I hope that there will be a hype. I'm also very sure that there will be. We will go through the valley of disillusionment also.
I was going to ask you. I was going to tell you good luck at the end to say, I hope you're going to, you and you as one of the driving forces are going to come out of the trough of disillusionment, I believe it's called, or whatever, the valley. Yeah.
That will certainly also come. And to some extent, we've been going through that ourselves already, kind of. So we've started indeed a couple of years ago. So Explain Data has been founded 6 years ago. And we have been very excited about what we can do. And as understanding cause and effect based on observational data, we have been going up the hype cycle also. And we have been going down into the valley of disillusionment, also kind of seeing where it's difficult, that we indeed need or to also involve the expert and finally come to a realistic approach, how to do causal discovery. So that's kind of our own hype cycle. And I think we now have a very good and realistic and practical offering in the context of causal discovery. And I would love to see it go up the hype cycle as well. And I hope we could get through the valley of disillusion, then also to arrive at a very realistic usage of causal discovery.
Very good. Final comment where we are with relation to causal discovery around the world. Is that the same for Germany, Europe, for USA, China, Asia, as well as the same as for specific markets? I think you suggested that maybe in healthcare, it may be the number one, the leading market. Any comment there, final?
Yeah, I think the situation isn't that difficult in the different parts of the world. I have the impression that topics like causality are a little bit more taught in US than in Germany, but that might be wrong. So at the end, if you go to certain machine learning courses on probabilistic reasoning, there's certainly a couple of sessions on causality, and there might be specific lectures on causality, but in general, it's very rare. I also hope that this, from a university point of view, is going to change. And from applying those algorithms to real-world data, I think we are definitely at the very beginning there. So there are a couple of different approaches on understanding cause and effect relationships. We are definitely not the only ones. There are just a few, but we are not the only ones, and it's very different approaches to it, more or less practical in a real-world setting. I think we have something which really works with real-world data and not just with artificial data. But I don't see that many differences in the different regions. With respect to industries, certainly healthcare is the industry which, since 100 years, already cares about causality. They need to. So if you develop a new product, a new treatment, you better make sure that it has cause and effect sense. And that's why healthcare, since 100 years already, does this in terms of randomized controlled trials largely. But what's becoming different is this huge amount of observational data, which simply are collected by means of how our healthcare systems work, electronic medical records, which are gathered increasingly, or data at public sickness funds. And those data are definitely still underutilized. And I see also in healthcare, I see it coming that real-world data, and with that, the topic of causal discovery is going to become more and more important. And the industry in manufacturing, I believe it's a little bit behind of healthcare in the context of understanding cause and effect, but definitely equally important. And there are also increasing amounts of data piling up. And at the end, I believe that the most comprehensive data and the biggest data sets at all are at the end coming from industry and from manufacturing lines. And that's why I believe there is a big opportunity in industry for us.
Michael, thank you very much. Yeah, I would agree. There's a big potential. Thank you. I would say those listeners, those companies in industry, typically that are interested in, trying out causal discovery, maybe with you, your company, they best, you told me, visit your website, explaindata.com. That's is with an X, PLAIN-data.com. Alternatively, you can always go to Michael Haft at LinkedIn, Michael Haft, Haft. Otherwise, if you, dear listeners, have any questions, comments, as always, please send a short email to Robert at aipod.de or Peter at aipod.de. Very happy that you stayed with us so far. Looking forward to have you again with us next time. And Michael, thank you very much. Very interesting topic. And as you suggested, we're probably at the beginning of it and looking forward to see what causal discovery will be doing with us and the industry in the next couple of years. Thank you.
Thank you, Peter, very much.